transducer, and basically we'll
So
have
can you
a
record the meeting?
okay. Recording has started. Okay, so yeah, so in this experiment we'll be measuring this angular displacement using a capacitive displacement transducer. So the capacitance of this transducer will be varying with theta, and we'll use that to uh, and we'll measure the capacitance value to get the value of theta. So this basically this transducer consists of two semicircular plates, and one of them is movable. So when we rotate the top plate, for example, uh, the overlap area also changes with the overlap angle, and so the so as the area changes, the capacitance between the two plates also changes, and it is given by this relation. And so now basically our task is to measure this capacitance values. So if we do that, we'll be able to measure the angle. So in order to measure this capacitance value, we use this circuit. Here this CX is basically that transducer, which and its capacitance value depends on theta. And um, this element here is the is an oscillator, so it generates a square wave output. And so when the output is high, this capacitor charges through this D2 diode, and when it is yeah, negative, the oscillator output, then uh, basically current flows from D1 to this capacitor to charge it in the opposite direction. And so as we can see that there will be some average current through this D2 in the right hand side direction, and then this part of the circuit basically removes the ripple from the output, and you'll have this amplifier at the output stage uh, to get the amplified output. And this is the experiment that you have to do, and you have to plot the measured values of the output of this charge pump versus this theta, and also this output voltage versus this theta. And you'll also have to derive a relation for these values and compare this measured values with the theoretical values. And you have to take into account the input offset voltage of the amplifier. And so this is the discussion portion. So you'll have to answer these all of these parts, and this is basically the experiment that you have to do. And if you need some reference for some details, you can have a look at this offline lab manual, but there are some mistakes here, so you have to be careful. Like these formulas might be wrong and this circuit diagrams might be wrong. So basically this is just for your reference, this part. You only have to do these things that are mentioned in page 2. This is the experiment.
Any question, guys, on this?
So what is the use of diode D1?
Yeah.
So
that's yeah.
So when this oscillator is generating a square wave output, so it varies from some positive voltage to some negative voltage. So when the voltage is negative, this capacitor gets charged through this D1 pathway. So this will be positive and this will be negative when this is negative, or oscillator output is negative. So so this paragraph basically describes although there are some errors here, so you'll have to find that out, and it is obvious, the errors are kind of obvious, and then you'll be able to derive. So one of the questions is to derive the uh, output voltage. So when you derive that, you'll get to know why we are using this D1 and D2 and everything.
Any questions on this? So one feedback I need from the general class, and while large portion of the class is missing from the theory, this thing only handful of you guys attend. So my question to you guys is, on the week of 22nd February, that's when I think the midsems are there, right? So essentially there are 2 more weeks to go towards the midsem. So the first question that I have is, all other theory courses that you have, so they will be having their exams during this week, right? Yes or no? That is the first question. Is the answer yes or no? Anyone, guys? Just answer this. Shubham, so Saurabh, you want
We
to
have not, yes, sir. Like we have not informed that test will be after 2 weeks. Like it is written in calendar, but like
Okay. So nobody has talked about this yet, right? Now the
yeah,
reason, now going to the second question, the reason why I asked this, right? Because some of these experiments that are given to you, or even the assignments that I'm given. So by the way, that also reminds me. So today is the last date for submitting your theory assignment. So hopefully, and please understand that your final grades, there will be weightage on the assignments as well. I've written that clearly in the email. I've told it in the class. I'm reminding again. So I hope you guys are preparing to submit the assignment. Is that okay? If you're not okay, please feel free to tell me that, sir, there is too much of pressure. Please tell me so that I understand. So Ayush, any comments? I was calling out random names. Ayush, Ayush, are you there? I can't hear you, Ayush.
Can you hear me now?
Yeah, yeah, yes, yes.
Hello.
Yes, go ahead, Ayush.
Actually, there is I don't know why my voice is not clearly audible. There it's clear.
It's clear now. Yeah. No, so the point
Okay.
is, my question is, are you people facing too much of difficulty in completing the assignment, or the labs are also being given, right? I hope you guys are able to take the load, right?
Yes, sir. Actually, the assignment is okay, but the PowerPoint is taking like little more time.
Yeah, so that is the reason I'm telling you guys, right? I mean, probably you can, I liked what group 6 did actually. They have divided the work, amongst themselves. It will not be a load if you divide the work. So assignment is okay, is what you are saying, right? Anyone else wants to say something on the loading that you are getting both from the theory class as well as from the lab? It is important I get some feedback on the loading because I don't want to push you guys too much. Okay. Um, somebody wanted to say, yes, go ahead.
So you asked us to plot the difference, so can I show that?
Okay, go ahead. So before we do that, so no more questions on this particular experiment, right? If any one of you have a question on the experiment, please feel free to reply to the email. You can do a reply all so that everyone in the class gets to see the question, or maybe you can put a question in the Teams also. and either one of the TA members, in this case it is actually Sanket, either he or me, we will get back to you with the answer, and you will receive the manual right away after the session today. Okay, go ahead. I think group 9.
Yes, sir. So this is that difference. It's coming around 32 millivolt. The difference
So it is
between
remaining
these
constant. So it is
two.
remaining
Yes,
constant,
it's
right?
constant.
Okay, fair enough. Fair enough. But the linearity, I think there was a significant difference between the linearity of group 6 and group 9. So that also, you can.
So that linearity thing also I can show.
Okay.
That if I plot it for like 270 to 350.
Mm-hmm.
Mm, like there is some difference. Like it's I plotted it. The range is 270 to 350. If I decrease it further,
Mm-hmm.
then it looks linear.
So, okay, so you are just saying that it's still a visual problem, it's not a real issue. That's what you guys are
Yes,
saying, right?
it's just it's like if I plot it like 270 to 330,
But
it's
there was,
coming out to be
there
straight.
was one, but there was one point that group 6 mentioned. It was the choice of the resistor values, the thermistor one and the ARM, R4 and R2. No, not that. R4 and R2, the values that they have chosen, that was different.
Yes, sir. So that also like won't make much difference. I tried it once, then I thought that they are
No,
also
just
getting the
check.
same.
Just
I
check. Yeah,
checked it once,
just
but
check.
I just undo the changes. So
The reason is the bridge constant. There is something called the bridge constant, right? That is
okay.
dependent on the resistor values.
Mm-hmm.
So there will be, maybe visually you may not be able to see the difference. Why don't you do one thing? Why don't you in the same graph, right? Plot for, so one resistor pair value you have taken R2 and R4, let's say 1K and something that you have taken, right? In the same
Yes.
graph, maybe what you can do is just make the, the values instead of 1K and this thing, right? I mean, whatever thermistor value you have taken, just make it 2 times or 4 times and see what happens.
Okay, sir. So like now only.
Yeah, if you can do now, then so be it.
Okay, okay.
Or why don't you do it, and then maybe what we will do, right? We'll probably, so there is still only 3:45. We'll ask one more group to kind of talk. That is okay, right? Yeah.
Mhm.
Um, so maybe, so let's see. I have not heard much from. So let's talk about then group 12 then. Yeah, let's do it in arithmetic progression. 6, 9, 12. So group 12, Shibham, Saurav, and Angana. Are you people there?
Yes, sir.
Okay, so can you, yeah, Angana, I need you to be a little bit louder, or maybe your microphone needs to be a little bit louder.
Okay, am I audible now, sir?
Yeah, now it is fine. So can you pull up your presentation and walk us through it?
Yes, sure, sir.
Yeah.
Sir, is my screen visible?
Yeah, it's visible. Go ahead.
Okay, so this is the presentation from group 12, which comprises Shivam, Saurabh, and me. Uh,
So all
so,
of you contributed in making the overall work. What was the
uh,
contribution from each one of you?
yes, sir. So I mostly did part one, and Shivam did part two, Saurabh did part three, and then we all kind of collaborated while
Oh,
making the PPT.
that's fine. That's fine. Okay, cool. Go ahead.
Yes,
Yeah,
sir.
this is fine. Go next page.
Yes, sir. So these are just the problem
Yeah,
statements.
yeah. Okay,
Coming
go
to
down.
this,
Yeah.
yes,
Oh, this
sir.
is also fine. Next page.
Okay, sir. So these are just the setup of the simulation for all the three parts. And
here again, I see the capacitor. Here again, I see the capacitor, which I think group 1, which Shubham was presenting.
yes, sir.
And it's the same value, 10 nanofarad. So why is that?
Yes, sir.
Actually, sir, we sort of took inspiration from our last semester's experiment. So this was more like in that experiment, the capacitor was present, and the reason given for that was that it limits the frequency response and amplifier oscillations. So that's why our circuits are more or less same.
I like your choice of words. It's Shivam, right?
Saurabh, sir.
Saurabh, okay. You took inspiration. That's good. It looks like a Hollywood or a Bollywood director talking, which is fine. So yes, so basically the capacitor has been placed for stability reasons. And if you were to do a Bode plot, you will find the answer pretty easily. And it is not because of noise that it has been placed. Typically for noise, right, we do not place discrete components for noise as such. When we are, I mean, I'm talking of device noise. I'm not talking of a large signal power supply noise or IO switching noise. I'm not talking of that. And noise by itself is a very complicated topic, meaning it has, again, multiple domains. Understanding needs to be there to understand, noise. Physics needs to be understood. Maths, meaning statistics, need to be understood, and electronics need to be understood. So we'll talk about noise in details, hopefully in some other, I don't know if, so that is another topic which is very close to my heart. But the point is we do not put discrete components to take care of noise as such. Care is taken inside. So for example, in the amplifier, or maybe it is the choice of the values, the resistor values, or the choice of the biasing current or the device sizes. That is what typically is done for noise, not much in terms of putting discrete components. So it is actually placed for stability reasons. Okay, go ahead.
Yes, sir. So actually, we were not like very sure about the stability part, like you said. So our major intent was the noise part only. But yeah, like you said.
Yeah. So one thing I think which none of the groups actually showed me, and I don't remember even the first group showing me, was actually a transient response of this circuit. All the groups showed me a DC, the output voltage varying with temperature. Now that is a DC analysis, right? Meaning where you are not considering that. So what would have been interesting to see is, let's say you are doing a power supply ramp up, right? Now somebody can say that, what do you mean by transient here, sir? Because we are measuring temperature. There is nothing associated as such with time, right? So that's a fair statement to make. But then, when we are powering up the chip, right? When you power up the TV or your computer, right? There is a certain settling behavior because of power up, right? So what would have been interesting to observe from the class would be somebody actually did a transient analysis. Somebody would have probably shown that maybe V1, which is 5 volt, the bridge power supply, if that was ramped up from, let's say, 0 to 5 volt, let's say in 100 microsecond, right? How would the output behavior look like? And if you probably plotted that, maybe in this case, of course, I don't know what is there inside the model of that amplifier. If it is a realistic model, probably you will see the importance of placing C1 in parallel with R4.
Okay, sir. Okay.
Okay. So this is for the full class, not just for the group 12, but carry on.
Okay, sir. So moving on to the results and discussion part. In part one, what we basically did was just kind of vary the temperature, and then we measured the current through the thermistor and made a note of the resistance value recorded. And this was the
This is good.
graph.
So this is good. Can you go back? Can you go back? Yeah. So this is another important thing. So probably this would bring back that question that I was asking, right? Why 1K and 10K and why not 1 meg or 1 ohm or something, right? So probably
Yes.
this is another very important practice as circuit designers, right? Typically, and this mistake happens even to the best of designers in the industry. what typically people just end up doing, right? Just look at the voltage profiles and say that things are okay. I mean, of course, we look at as maximum as possible, but it is very important to actually look at the current profile, the current values flowing through the elements, and ensuring that none of the current values are funny, meaning none of it falls, in an unreasonable range of becoming too high or too low. So that is a very important practice as circuit designers or electronic system engineers. Please ensure that going ahead, right, if you are analyzing circuits, it's not just about the voltage behavior, but also the current behavior. Another, in the same context, when you are powering up the circuit, it's very important to look at powering up and powering down both. It's very important to look at the current or the power consumed by the chip or by the system, because typically what happens because of problems when you power up the supply, right, that's when things are not very well defined. So when we talk of an amplifier, we say the amplifier operating range must be, the devices inside the amplifier must be in saturation so that the amplifier behaves linearly and blah blah blah, right? But the key thing to note is during power up, things are not under our control, right? Meaning the power supplies can vary widely. So as designers, we take a lot of care to ensure that when the circuits are powering up, it does not create device failures. It should not create that when you are powering up, it starts drawing, let's say, a circuit designed to, in the steady state, it takes current in milliamperes. But when it is powering up, it starts taking currents in amperes, because then the power supply is going to be screwed up, right? So it's going to be messed up big time, right? So we need to ensure, these key things, and I like the fact that this group has taken care to actually look at the current values. So good job, group 12. Okay, carry on.
Okay, yes, sir. So now plotting the resistance value when temperature changes, this is the plot that we obtained, and as we can see, there is an exponential relation between the resistance of the thermistor and temperature, and also the value of basically the curvature will depend on the value of beta, which for our experiment we have taken as 3500. Now moving on to part 2, this is where we derived the expression for output voltage in terms of temperature.
Yeah,
Right.
very good. Go ahead.
Yeah.
No, that's fine.
Sir,
Skip it.
so
Okay. Yeah,
okay.
yeah. Go
Okay,
ahead.
sir. So in this slide, we have tried to calculate the sensitivity to maximize the sensitivity. So we use the whole V out obtained in the previous slide and differentiated with respect to temperature. And then after the differentiation, we got this equation. So we needed to choose the values of R1, R2, R3 in such a way such that we get maximum sensitivity. So from doing the calculation, we found that R1 must be equal to RNTC, that is the thermistor resistance, but it cannot be the same because RNTC will vary with temperature. That's why we chose the value of R1 as average of RNTC in the temperature range. So,
average in the temperature range, right? That's what you mean.
Yeah.
Okay.
Yeah. And then in second part, this is the graph for the temperature range from 295 to 325 Kelvin, and and this is the plot for the same, and we did that's the thing. So.
Okay, cool. Next slide. Non-idealities also you have covered here. The delta V out. You have plotted temperature versus error. Yeah, so basically, okay. So typically when you're talking of error, right, we'll talk in terms of the percentage error, percentage terms of the same variable that we are measuring, right? So I don't think you guys have done it like that, right? You have on the y-axis when you have the error is shown is in voltage. Is that correct or?
Yes, sir. It's in voltage.
Yeah, so that is not a good practice. Typically, when we talk of errors, right? So we are measuring temperature. So what ideally we should do is get the temperature that the circuit is showing. So let's say the input temperature that you have given is, let's say, 300 Kelvin, and let's say the circuit is giving us 305 or maybe 295 or whatever. So we should calculate the percentage error based on the measurement parameter itself, right?
Okay, right, sir.
Okay, so this is also done. Okay, so let's go to quickly to another one. I mean, we have we'll spend another 15 minutes time. So this is group 12, right?
Yes,
Okay,
sir.
so good job, guys. So good. So see, from each of the groups, right, we are able to learn something new, right? Which is the goal of learning from each other. So let's see. So that we have done group 1 also. So okay, so let's take maybe group 3. Ajay, Ram, Meena, Anish, Paul, and Arpit.
Yes, sir.
You guys are there? You can present? You can walk us through your slides?
Okay, sir. I will present.
You're not very happy presenting, or the way you said okay looks like you're not very happy?
No, sir. That
You're not happy? You're happy?
I mean, it's fine.
Okay, it's fine. Okay.